What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. This video is an introduction to limits for those first learning about limits, and we're going to really focus on the concept and the definition of a limit. We're going to look at different representations like graphs, tables, and functions, so let's jump right into it. Alright, so this is a rational function. It's a very common type of function we work with when we're talking about limits, and this is because they have interesting discontinuities like holes and asymptotes. For example, if I try to plug 2 into this function, try to figure out f of 2, in the numerator I get 2 squared, which is 4, plus 2 minus 6. In the denominator, I get 2 squared, which is 4, minus 6 times 2, that's 12, plus 8. So the numerator simplifies to 0, as well as the denominator. This means that the function is undefined at 2. Doesn't matter if 0 is also in the numerator, 0 is in the denominator, we cannot divide by 0. The function is undefined at 2. So we have no idea what this function looks like when x equals 2, but maybe we want to figure out what it looks like around that area. So what we can do is we can plug in x values a little bit less than 2, so we can get an idea of what the function looks like around 2. So a little bit less than 2, another way to think of it is to the left of 2, right? Because on a number line, numbers less than 2 are to the left. So for example, we could plug in 1.9, 1.99, and 1.999, and what we're doing is we're getting closer to 2 from the left to see what happens to these y values. So if we plug these numbers into a calculator, into the function, here's what we get rounded at 3 decimal places. And now what we can observe is that as x gets closer to 2 from the left, the y values seem to be getting closer to negative 2.5. This is the concept of a one-sided limit, and we can write this using limit notation as the limit as x approaches 2 from the left of this function equals negative 2.5. So we know what the function looks like really close to 2 to the left, and now we can do the same thing to the right. So let's look at it. To the right of 2 is 2.1, and we can get closer to 2 from the right by plugging in 2.01 and 2.001. And what we do when we plug these into a calculator is we can observe that although the numbers are now bigger, right, they are decreasing as we move to the left, they seem to also be approaching negative 2.5. That is, the limit as x approaches 2 from the right of this function also equals negative 2.5. So we use the little plus again in the sort of exponent position to denote from the right. One way to remember that is from the really big positive numbers, and we use the minus symbol again in that sort of exponent position to say the limit from the left. These are each one-sided limits, really important concepts to understand. And this is a really important theorem, the limit existence theorem, where we can talk about a two-sided limit, which we often just call a limit. So if we're saying find the limit of something, we're referring to a two-sided limit. And here's how we write it. We just don't include any plus or minus. We just write 2. So the limit as x approaches 2 of this function. And it turns out that if the left and right hand limits both exist and equal the same real number, then the two-sided limit exists and equals that real number. So what this means is that we can approach 2 from the left or from the right, and in either case, as we do that, the y values get closer and closer to negative 2.5. Alright, so let's summarize some things we've learned. First is notation. This is how we write limits. The limit as x approaches a of f of x equals L. And here's a really good informal way of thinking about the definition. I say informal because there's a precise definition that you might not learn in AP Calculus, but this is a great informal way of thinking about it. The limit is the number that the y values get closer to as x gets closer and closer to a. So in the previous example, our a value was 2, and as x got closer to a from the left or from the right, the y values got closer to negative 2.5. And that's why that was the limit. This is a great way of thinking about the limit. As x approaches some number, what do the y values seem to approach? Finally, we touched on this theorem. The limit exists, the two-sided limit exists and equals L, if and only if the left and right-sided limits also exist and equal L. So there are two ways mainly two ways we apply this theorem. And one is trying to figure out what a limit is or if it exists. And we often do that by checking the left limit, checking the right limit, and seeing if they equal the same number. And if they do, we can say the limit exists and equals that number. Another way is to show a limit doesn't exist. If we find the left-hand limit and find the right-hand limit, and those are different numbers, then we can say that the limit does not exist. Or if one of them does not exist, then we can say the limit does not exist. Let's look at another example in a table. This time I have it all filled in. This is a function represented in table form. And let's look at the left-hand limit, the limit from the left as x approaches -1. And let's look at the limit from the right as x approaches -1. So again, the way we are thinking about this is the limit from the left. As the x values get closer to -1 from the left, what do the y values seem to be getting closer to? And I think a good approximation is 4 for this. They seem to be getting closer to 4. From the right, as the x values get closer to -1 from the right, what do the y values seem to be getting closer to? And that seems to be 2 as a good approximation. So what we can say from this is that since the left-handed limit is 4 and the limit from the right is 2, that the limit itself does not exist because 4 and 2 are not equal. And that's what we just learned from our limit existence theorem. These two things have to be exactly the same in order for the general limit to exist. So let's write a sentence to justify this. Since, and we can say the limit from the left, the limit as x approaches 1 from the left does not equal the limit as x approaches -1 from the right, the limit, the two-sided limit, or just the limit, does not exist. And that's what we can conclude from the left and right limit that we just found. Awesome. Hopefully that's making sense. Let's look at a graph. Very common type of representation that we see and we're asked to find limits of. And they're often crazy graphs like this with jumps, holes, asymptotes, different stuff going on. So let's look at this. We're going to find the limit as x approaches -5 from the left, from the right, the two-sided limit, and then f of -5, which means the y value when x is -5. Let's start at the top. So here's our strategy. We're going to find -5 on the x-axis. That's right here. We're going to move a little bit to the left since we're finding the limit from the left. We're going to go a little bit to the left and we're going to find the function, which is down here, a little bit to the left. And then we're going to approach -5 from the left. And as we are tracing along this function, approaching -5 from the left, we're going to be looking at the y-axis and looking at what y value do we seem to be getting closer and closer to as we get closer and closer to -5. That seems to be -2. So let's go and write -2 here. Same thing, limit from the right, we're going to find -5, we're going to move a little to the right, we find the function, and then we trace coming from the right along the function, and we look for the y value that we're getting closer to, which is 7. So now again, we're applying that limit existence theorem. The limit from the left is -2, from the right is 7, and so the limit does not exist. All right, finally, what is the y value when x is -5? Well, let's find -5, and we're looking for where the function is filled in. So here's a hole. The function is not defined up here at -5, but it is defined down here at -5. So this y value is -2. All right, let's look at the same function. This time we're approaching a different number, and that's -3. From the left, from the right, two-sided, and then we're finding the y value at -3. So I encourage you at this point, pause the video, try this on your own, then use the video to check your answer. All right, hopefully you did some good work on your own. Same strategy, we're going to find -3, go a little to the left, find the function. As we get closer and closer to -3 from the left, the y values seem to be getting closer to 5. Same thing to find the right-handed limit, find -3, move a little bit to the right, find the function, it's up here. We're going to trace along the function from the right, and it seems like the y values are approaching 5 as well. So now what's cool about this is for the two-sided limit, if we find the left and right-hand limits, we don't really need to look back at the graph. We can just look up at each of the two-sided limits, say, are they equal? If they are, that's the limit. If they're not, then it's D and E like the last example was. So this limit is 5. We can approach from either side, left, right, In both cases, the y values get closer to 5. Finally, what is f of negative 3? What is the y value when x equals negative 3? Well, let's go here at negative 3. If we go up, well, there's a hole there. The function isn't defined there at negative 3, but it is defined way down here, right, at negative 6. So that hole is sort of filled in way down here, and that's a thing that's sometimes going to happen. So the y value at negative 3 is different from the limit, and that's totally fine because limits aren't about what happens at this particular x value. It's about what happens as we get closer and closer to it from the left and from the right. So to really hammer in that idea, let's look at 3 more examples. Here's one example. Let's find the limit as x approaches 2, and this is a two-sided limit. So we're going to compare the left-hand limit, compare the right-hand limit. And in this case, this example is actually, it's kind of funny. My students struggle with this because it's so simple. They're so used to looking at holes and asymptotes and jumps, where this limit is actually just 2, right? This y value 2 as we approach from the left, as we approach from the right. In either case, the y values get closer and closer to 2. That limit's just 2. Here, this time we have a hole. The function is not defined at 2, where in this previous case the function was, right? F of 2 is also 2. And this is in fact what it means for a function to be continuous, is that the limit exists, the function's defined, and those two things are equal to each other, which I'll get into in another video. In this case, the function is not defined at 2, but the limit still exists and the limit still equals 2. So again, hammering in this idea that for limits, we don't care about what's happening at 2, where x equals 2 exactly, only around it. As we approach from the left and we approach from the right, the y values get closer to 2. Finally, the function could be defined in some other place, right? In this case, f of 2 is defined. It wasn't in the last example, it is this time, but it's negative 3. Way down here, there's this single point. However, the limit from the left and the limit from the right are still each 2, and so the two-sided limit is 2. So we saw 3 examples, one where the function's defined but it's not equal to the limit, one where the function isn't defined but the limit still exists and equals that number, and another where the function's defined and it equals exactly what the limit is. And again, in all of these cases, I'm just kind of hammering in that idea. We don't care what happens at 2, only what happens as we get close to 2, and that's the idea of a limit. Hopefully this video helped you gain some understanding. Like, comment, subscribe, do all that stuff. But most importantly, keep flexing those brain muscles. I'll see y'all later.